Have you ever talked to your phone and had it understand you? Asked your smart speaker to play your favorite song? Or wondered how Netflix suggests movies you might enjoy? These everyday wonders are powered by a technology called deep learning. Deep learning is changing the world around us, often in ways we barely even notice. It's the technology that allows computers to learn from vast amounts of data, mimicking how our own brains work. Deep learning is the engine behind facial recognition, allowing your phone to unlock with a glance. It's what lets self-driving cars navigate busy streets, and it's how online retailers seem to know your taste better than you do. But how does it all work? What's happening inside these machines that makes them seem so intelligent? This essay will take you on a journey into the world of deep learning, unraveling its mysteries and exploring its incredible potential. We'll start with the basics, explaining what deep learning is and how it's different from other types of artificial intelligence. Then we'll delve into the history of this fascinating field, tracing its roots back to the early days of computer science. Deep learning is a subfield of machine learning, which itself falls under the umbrella of artificial intelligence. While artificial intelligence aims to create machines that can perform tasks typically requiring human intelligence, machine learning focuses on algorithms that allow computers to learn from data without explicit programming. Deep learning takes this a step further. At the heart of deep learning are artificial neural networks, complex structures designed to mimic the intricate workings of the human brain. These networks consist of interconnected nodes or neurons organized in layers. Each connection between neurons has a weight assigned to it, representing the strength of the connection. During the learning process, these weights are adjusted, allowing the network to identify patterns and make predictions based on the data it's been trained on. The deep learning refers to the use of multiple layers in these neural networks. This depth allows the network to learn increasingly abstract representations of the data, leading to more accurate and sophisticated predictions. For example, in image recognition, the first layers of a deep neural network might learn to detect simple edges and patterns, while deeper layers learn to identify more complex features like shapes, objects, and even faces. Imagine training a deep learning model to recognize different dog breeds. Initially, the model might only differentiate between colors and basic shapes. As it processes more images, it begins to recognize patterns unique to each breed, such as ear shape, tail length, or fur texture. The more data it receives, the more refined its understanding becomes, allowing it to classify even the most subtly different breeds with remarkable accuracy. The roots of deep learning can be traced back to the mid-20th century, a time when the very idea of artificial intelligence was still in its infancy. In 1957, Frank Rosenblatt, an American psychologist and computer scientist, invented the perceptron, a type of artificial neuron that laid the groundwork for modern neural networks. The perceptron was designed to mimic the behavior of a single biological neuron, receiving inputs, processing them, and producing an output based on a simple threshold. While the perceptron showed early promise, its limitations soon became apparent. It struggled to learn complex patterns and was incapable of solving problems that required multiple layers of processing. This led to a period known as the AI winter in the 1970s, where funding and interest in artificial intelligence research waned. However, the seeds of deep learning had been sown, and a resurgence was on the horizon. In the 1980s, a breakthrough came with the development of backpropagation, a powerful algorithm for training multi-layered neural networks. Backpropagation enabled researchers to effectively adjust the weights of connections between neurons, allowing networks to learn more complex patterns from data. This marked a turning point, breathing new life into the field of deep learning. Despite these advancements, deep learning still faced significant challenges. Training large neural networks required immense computational power and vast amounts of data, both of which were scarce at the time. It wasn't until the 21st century, with the advent of powerful GPUs, graphics processing units, and the explosion of digital data, that deep learning truly took off. At the core of deep learning are artificial neural networks, intricate webs of interconnected nodes that process and learn from data. These networks are inspired by the biological neural networks found in our brains, where neurons communicate with each other through electrical and chemical signals. Just as our brains learn from experience, artificial neural networks learn from the data they are trained on, adjusting their internal parameters to improve their performance. A typical artificial neural network consists of multiple layers of neurons, each performing a specific type of computation. The first layer, known as the input layer, receives the raw data, such as pixels in an image or words in a sentence. This data is then passed through one or more hidden layers, where increasingly complex features and patterns are extracted. Finally, the output layer produces the network's prediction or decision. The connections between neurons in a neural network are associated with weights, numerical values that determine the strength of the connection. During the learning process, these weights are adjusted based on the network's performance, allowing it to fine-tune its responses and improve its accuracy. This process of weight adjustment is guided by algorithms, mathematical recipes that steer the network towards finding the optimal set of weights for a given task. The magic of deep learning lies in the network's ability to learn hierarchical representations of data. In other words, as data flows through the layers of the network, increasingly abstract and meaningful features are extracted. For example, in image recognition, the first layers might learn to detect edges and corners, while deeper layers learn to identify more complex shapes, objects, and even faces. Section 5. Training the machine mind, algorithms and optimization. Training a deep learning model is akin to teaching a child to ride a bike. At first, the child stumbles, wobbles, and requires constant guidance. With practice and feedback, however, the child gradually learns to balance, steer, and pedal, eventually mastering the skill. Similarly, a deep learning model learns through a process of trial and error, guided by algorithms and feedback mechanisms. One of the most common algorithms used to train deep learning models is called gradient descent. Imagine a hiker trying to find the lowest point in a valley. The hiker starts at a random location and takes small steps in the direction of the steepest descent. Similarly, gradient descent starts with an initial set of weights for the neural network and iteratively adjusts these weights in the direction that minimizes the error between the network's predictions and the actual target values. During training, the deep learning model is fed with a large dataset, divided into smaller batches. For each batch of data, the model makes predictions and compares them to the ground truth. The difference between the predictions and the actual values is measured using a loss function, which quantifies the model's error. The goal of the training process is to minimize this loss function, bringing the model's predictions as close as possible to the true values. The process of training a deep learning model can be computationally expensive and time-consuming, especially for complex tasks and large data sets. To accelerate the training process, researchers and engineers employ various optimization techniques. These techniques aim to find the optimal set of model parameters more efficiently, reducing the time and resources required for training. Section 6. Deep Learning in Healthcare, Transforming Diagnosis and Treatment. Imagine a world where diseases could be detected earlier, diagnoses were more accurate, and treatments were tailored to each patient's unique needs. This is the promise of deep learning in healthcare, a field rapidly transforming how we approach medicine. From analyzing medical images to predicting patient outcomes, deep learning algorithms are revolutionizing healthcare at an unprecedented pace. One of the most impactful applications of deep learning in healthcare is in medical imaging. Deep learning models, particularly convolutional neural networks, CNNs, excel at analyzing images and identifying patterns that might escape the human eye. These models can be trained on massive data sets of medical images, such as X-rays, Connecticut scans, and MRIs, learning to detect subtle anomalies that indicate the presence of diseases like cancer, pneumonia, and Alzheimer's. The benefits of using deep learning in medical imaging are manifold. Deep learning algorithms can assist radiologists in making faster and more accurate diagnoses, reducing the risk of human error and potentially saving lives. Moreover, these algorithms can identify patterns and predict outcomes, helping doctors personalize treatment plans and improve patient care. Beyond medical imaging, deep learning is being applied to a wide range of healthcare challenges. Deep learning models are being used to predict hospital readmissions, identify patients at risk of developing chronic diseases, and even discover new drug targets. As deep learning technology continues to advance, its potential in healthcare seems limitless, promising a future where diseases are diagnosed earlier, treatments are more effective, and patient outcomes are significantly improved. Section 7. Autonomous Vehicles, Navigating the Future with Deep Learning. Self-driving cars, once a futuristic concept confined to science fiction, are rapidly becoming a reality, thanks in large part to the power of deep learning. Deep learning algorithms are the brains behind autonomous vehicles, enabling them to perceive their surroundings, make decisions, and navigate complex environments without human intervention. Autonomous vehicles rely on a suite of sensors, including cameras, LiDAR, and radar, to collect data about their surroundings. This data is then fed into deep learning models, which process the information and make sense of the environment. Convolutional neural networks, CNNs, are particularly well suited for analyzing visual data from cameras, allowing the vehicle to detect and classify objects such as pedestrians, other vehicles, traffic lights, and road signs. Once the environment is perceived, deep learning algorithms come into play again to make driving decisions. Reinforcement learning, a type of deep learning that learns through trial and error, is often used to train autonomous vehicles to navigate safely and efficiently. In reinforcement learning, the algorithm learns by interacting with its environment and receiving rewards for desirable actions, such as staying within lane markings and avoiding collisions. The development of autonomous vehicles is a complex and challenging endeavor, requiring expertise in various fields such as robotics, computer vision, and artificial intelligence. However, the potential benefits of self-driving cars are immense. Autonomous vehicles promise to improve road safety by reducing accidents caused by human error, increase accessibility for individuals who are unable to drive, and enhance transportation efficiency by reducing traffic congestion. Section 8. The Power of Understanding. Deep Learning in Natural Language Processing. Language, the very foundation of human communication, has always posed a significant challenge for computers. However, deep learning is rapidly bridging the gap between humans and machines, enabling computers to understand and process human language with remarkable accuracy. This field, known as natural language processing, or NLP, is revolutionizing how we interact with technology, from chatbots and virtual assistants to language translation and sentiment analysis. Deep learning models, particularly recurrent neural networks and transformers, are designed to process sequential data like text and speech, making them ideal for NLP tasks. These models can be trained on massive text datasets, learning the intricacies of grammar, syntax, and semantics, enabling them to understand the meaning and context of human language. One of the most widely known applications of deep learning in NLP is in machine translation. Deep learning models have significantly improved the accuracy and fluency of machine translation systems, making it easier for people to communicate across language barriers. Another transformative application is in sentiment analysis, where deep learning models can analyze text data, such as social media posts and customer reviews, to determine the underlying sentiment, whether positive, negative, or neutral. The advancements in deep learning-powered NLP are transforming how we interact with technology and each other. Virtual assistants like Siri and Alexa are becoming increasingly sophisticated, understanding our commands and responding in a more natural and human-like manner. Chatbots are being deployed in customer service, providing instant support and resolving queries efficiently. Section 9. Beyond Imagination. Deep Learning's Expanding Horizons. As we've explored, deep learning is already transforming industries like healthcare, transportation, and communication. However, the potential applications of deep learning extend far beyond these domains, reaching into realms previously considered the exclusive domain of human creativity and intuition. From composing music and generating art to designing new materials and accelerating scientific discovery, deep learning is pushing the boundaries of what's possible. In the realm of art and creativity, deep learning algorithms are demonstrating an uncanny ability to generate original music, paintings, and even poetry. Generative Adversarial Networks, or GANs, a class of deep learning models known for their ability to create realistic synthetic data, are being used to generate stunning works of art that mimic the style of famous painters or compose music that evokes specific emotions. Beyond artistic expression, deep learning is making significant contributions to scientific discovery and technological innovation. In drug discovery, deep learning models are being used to analyze massive data sets of molecular structures, identifying potential drug candidates, and accelerating the development of new treatments for diseases. In materials science, deep learning is aiding in the design of new materials with enhanced properties, such as strength, durability, and conductivity. The rapid advancements and expanding applications of deep learning are a testament to its transformative potential. As deep learning technology continues to evolve, we can expect even more groundbreaking applications to emerge, blurring the lines between human ingenuity and artificial intelligence and shaping the future in ways we can only begin to imagine. Section 10. Peering into the network. The architecture of deep learning. Imagine a deep learning model as a vast, intricate factory, buzzing with activity as raw materials are transformed into finished products. This factory, like its real-world counterpart, is meticulously organized, with specialized units working in concert to achieve a common goal. These units are the layers of a deep neural network, each playing a crucial role in processing information and extracting meaningful patterns from data. The journey begins at the input layer, the network's gateway to the outside world. Here, raw data, such as pixels in an image or words in a sentence, are fed into the network, marking the start of their transformation. The input layer acts as a receptionist, receiving and organizing the data before passing it on to the next stage of processing. From the input layer, data flows through a series of hidden layers, the network's internal processing units. These layers are where the true magic of deep learning unfolds. Each hidden layer consists of numerous interconnected nodes or artificial neurons that perform mathematical operations on the data received from the previous layer. These operations, often involving weighted sums and activation functions, allow the network to extract increasingly complex and abstract features from the data. The number of hidden layers in a deep neural network can vary depending on the complexity of the task at hand. Shallow networks with only a few hidden layers are suitable for simpler tasks, while deep networks with dozens or even hundreds of hidden layers are required for more challenging problems. The depth of a network allows it to learn hierarchical representations of data, with each layer building upon the knowledge extracted by the layers before it. Imagine teaching a child to recognize different animals. You might start by showing them pictures of cats and dogs, pointing out their distinctive features. With enough exposure and feedback, the child begins to form mental models of these animals, learning to distinguish between them based on their appearance. Similarly, a deep learning model learns to make sense of data through a process of training, guided by algorithms and fueled by vast amounts of labeled data. The training process begins by feeding the deep learning model with a labeled dataset, where each data point is paired with its corresponding target value. For example, in image classification, the dataset might consist of thousands of images, each labeled with the object it depicts. The model's task is to learn the relationship between the input data and the target values, enabling it to make accurate predictions on unseen data. During training, the model's internal parameters, namely the weights and biases associated with the connections between neurons, are iteratively adjusted to minimize the difference between its predictions and the true target values. This adjustment is guided by a loss function, a mathematical formula that quantifies the model's error. The goal of the training process is to find the set of parameters that minimizes this loss function, indicating that the model has learned to make accurate predictions. The training process is typically iterative, with the model processing the dataset multiple times. Each pass through the entire dataset is called an epoch. Within each epoch, the dataset is divided into smaller batches, and the model's parameters are updated after processing each batch. This iterative process allows the model to gradually improve its performance, refining its internal representations of the data and reducing its error rate. Deep learning models, for all their complexity, rely on a surprisingly simple yet powerful language of learning, governed by weights, biases, and loss functions. These mathematical entities act as the building blocks of the learning process, shaping the network's understanding of data and guiding it towards making accurate predictions. Weights, as the name suggests, determine the importance or strength of the connections between neurons. Each connection in a neural network has an associated weight, representing how much influence the output of one neuron has on the input of another. During training, these weights are adjusted, amplifying or attenuating the flow of information through the network, allowing the model to discern salient patterns from noise. Biases, on the other hand, act as thresholds that influence a neuron's tendency to fire or activate. Each neuron has a bias term that shifts its activation function, making it more or less sensitive to its inputs. Biases introduce a level of flexibility into the network, allowing it to model more complex relationships between inputs and outputs. The loss function serves as the model's compass, guiding it towards the optimal set of weights and biases. It measures the discrepancy between the model's predictions and the true target values, providing a quantitative assessment of the model's error. The choice of loss function depends on the specific task at hand, with different functions suited for classification, regression, and other machine learning tasks. During training, the deep learning model strives to minimize the loss, adjusting its weights and biases in the direction that reduces the error. This process, often visualized as navigating a multidimensional landscape in search of the lowest point, continues until the model converges on a set of parameters that yield satisfactory performance. Imagine a sculptor meticulously chiseling away at a block of marble, gradually revealing the intricate details of a masterpiece hidden within. Similarly, backpropagation, a cornerstone algorithm in deep learning, acts as a sculptor of sorts, fine-tuning the network's weights and biases to achieve optimal performance. Backpropagation, short for backward propagation of errors, is an iterative algorithm that propagates error signals from the output layer back through the network to the input layer. This backward flow of information allows the algorithm to identify which weights and biases contributed most to the model's errors and adjust them accordingly. The process begins by calculating the error at the output layer, which represents the difference between the model's predictions and the true target values. This error is then propagated backward through each layer, using the chain rule of calculus to calculate the gradient of the loss function with respect to each weight and bias. The gradient, in essence, indicates the direction and magnitude of change required for each weight and bias to minimize the loss function. Armed with this information, the algorithm updates the weights and biases, nudging the model towards making more accurate predictions. Backpropagation, through its iterative process of error calculation and parameter adjustment, acts as the driving force behind the learning process in deep neural networks. It allows these complex models to learn from their mistakes, refining their internal representations of data and gradually improving their ability to make accurate predictions. Having explored the fundamental principles of neural networks, we now venture into the realm of specialized architectures, each tailored to excel in specific domains. Just as different tools are designed for specific tasks, these specialized neural networks address the unique challenges posed by different types of data and learning objectives. One size does not fit all in the world of deep learning. While the basic principles of neural networks hold true, their architecture, the arrangement of layers and connections, can be adapted to better suit the nature of the data being processed. For example, images, with their spatial structure and local patterns, require a different approach than sequential data like text or time series, where order and context are paramount. This need for specialization has led to the development of a diverse family of neural network architectures, each with its strengths and weaknesses. Convolutional neural networks, or CNNs, excel at processing visual data, leveraging their ability to detect patterns regardless of their position in the input. Recurrent neural networks, or RNNs, on the other hand, are designed to handle sequential data, capturing dependencies and temporal relationships between elements. This specialization extends beyond CNNs and RNNs. Generative adversarial networks, or GANs, have emerged as powerful tools for generating synthetic data, while autoencoders excel at data compression and reconstruction. The world of deep learning is a constantly evolving landscape, with new architectures and variations emerging to address specific challenges and unlock new possibilities. Section 15. Convolutional neural networks, mastering the art of visual recognition. Imagine trying to understand a scene in a photograph. Your eyes naturally scan the image, picking out objects, recognizing faces, and discerning the relationships between different elements. Convolutional neural networks, or CNNs, inspired by the visual cortex of the human brain, excel at this very task, mastering the art of visual recognition through their unique architecture. CNNs employ a specialized type of layer called a convolutional layer, which acts as a sliding window, scanning the input image for specific features. These features, represented by small grids of weights called filters or kernels, detect patterns such as edges, corners, and textures. As the convolutional layer slides across the image, it produces a feature map, highlighting the locations and intensities of these features. The key to CNN's effectiveness lies in their ability to learn hierarchical representations of visual data. Early convolutional layers learn to detect simple, low-level features, while deeper layers combine these features to identify more complex patterns, such as shapes, objects, and even faces. This hierarchical approach allows CNNs to build up a rich understanding of the visual world, much like our own brains do. Pooling layers, interspersed between convolutional layers, play a crucial role in reducing the dimensionality of the feature maps, making the network more computationally efficient and robust to variations in the input image. These layers downsample the feature maps, preserving the most salient information while discarding irrelevant details. The final layers of a CNN are typically fully connected layers, which aggregate the information extracted by the convolutional and pooling layers, producing a high-level representation of the image. This representation is then fed into a classifier, such as a softmax layer, which assigns a probability to each possible class label, allowing the CNN to make predictions about the image's content. Section 16. Recurrent neural networks, navigating the streams of time. Time, with its relentless flow, shapes our experiences, influencing our thoughts, actions, and perceptions. Recurrent neural networks, or RNNs, unlike their feed-forward counterparts, possess a unique ability to process sequential data, capturing temporal dependencies and understanding the unfolding narratives embedded within. RNNs achieve this temporal awareness through their recurrent connections, forming loops that allow information to persist and influence future outputs. Unlike a traditional neural network, where information flows in one direction from input to output, RNNs have connections that feed the output of a neuron back into itself, creating a form of memory within the network. This internal memory allows RNNs to keep track of past inputs, understanding the context and dependencies within a sequence. For example, in language modeling, an RNN can predict the next word in a sentence by considering the words that came before it, capturing the grammatical structure and semantic meaning of the text. However, traditional RNNs suffer from a limitation known as the vanishing gradient problem, making it difficult for them to learn long-range dependencies in sequences. To address this, more sophisticated RN architectures, such as long short-term memory networks, or LSTMs, and gated recurrent units, or GRUs, have been developed. LSTMs and GRUs introduce gating mechanisms that regulate the flow of information through the network, selectively remembering or forgetting information from previous time steps. These gates, controlled by learnable parameters, allow the network to capture long-range dependencies, making them suitable for tasks involving longer sequences, such as speech recognition, machine translation, and time series prediction. Section 17. Expanding the toolkit GANs, autoencoders, and beyond. The world of deep learning is a vibrant and ever-evolving landscape, with new architectures and techniques emerging to address specific challenges and push the boundaries of what's possible. Beyond the foundational concepts of CNNs and RNNs, a rich tapestry of specialized neural networks awaits, each with its own unique strengths and applications. Generative adversarial networks, or GANs, for instance, have taken the world by storm with their ability to generate realistic synthetic data, from images and videos to music and text. GANs consist of two competing neural networks: a generator, tasked with creating realistic data, and a discriminator, trained to distinguish between real and generated data. This adversarial process, akin to a counterfeiter trying to create fake money that can fool a detective, drives both networks to improve their abilities. The generator learns to create increasingly realistic data to fool the discriminator, while the discriminator becomes more adept at identifying subtle flaws in the generated data. Autoencoders, on the other hand, excel at data compression and reconstruction, learning to represent complex data in a lower dimensional space while preserving its essential features. Autoencoders consist of an encoder network, which compresses the input data, and a decoder network, which reconstructs the data from the compressed representation. This ability to learn compressed representations makes autoencoders valuable for tasks such as data denoising, anomaly detection, and image generation. By learning the underlying structure of the data, autoencoders can identify and remove noise, detect outliers that deviate from the norm, and even generate new data that resembles the training data. The world of deep learning is filled with such innovative architectures, each pushing the boundaries of what's possible with artificial intelligence. As researchers and engineers continue to explore new frontiers, we can expect even more specialized and powerful neural networks to emerge, unlocking new possibilities and shaping the future of technology. Section 18. The future unfolds. Deep learning's transformative potential. As we conclude our exploration of deep learning, we stand at the cusp of a new era, one where intelligent machines are no longer a figment of science fiction, but a tangible reality. Deep learning, with its ability to extract knowledge from data and make intelligent decisions, has emerged as a driving force behind this technological revolution, transforming industries, accelerating scientific discovery, and reshaping our interaction with the world around us. From healthcare to transportation, finance to entertainment, deep learning is permeating every facet of our lives. In healthcare, it's enabling earlier disease detection, personalized treatments, and drug discovery at an unprecedented pace. Self-driving cars, powered by deep learning algorithms, promise to make our roads safer and more efficient, while in finance, these algorithms detect fraud, optimize investments, and provide personalized financial advice. The true potential of deep learning, however, extends far beyond these current applications. As deep learning models become more sophisticated, capable of handling even larger and more complex data sets, we can expect to see breakthroughs in fields as diverse as materials science, climate modeling, and fundamental physics. Imagine deep learning algorithms designing new materials with tailored properties, predicting extreme weather events with greater accuracy, or unraveling the mysteries of the universe by analyzing vast astronomical data sets. The journey of deep learning has just begun, and the road ahead is filled with both exciting possibilities and daunting challenges. As we navigate this uncharted territory, it's crucial to consider the ethical implications of intelligent machines, ensuring that these technologies are developed and deployed responsibly for the benefit of all humankind. The future unfolds before us, shaped by the transformative power of deep learning, and it's up to us to harness this power wisely, creating a future where intelligent machines augment human capabilities, solve our most pressing challenges, and unlock a new era of progress and prosperity.